Well, welcome back, ladies and gentlemen. Hello, Mr. Eicher here, coming at you with the second part of lesson 4.5b about solving polynomial equations. We'll look at an example of the sum of two cubes pattern, which you learned yesterday or the day before. We'll look at factoring four terms, and then we'll look at a word problem. So let's get started. The sum or difference of two cubes pattern. The top one is the sum with the plus, and the bottom one is the difference with the minus. You learned these recently, so it's going to be really helpful that you have those handy. To factor something that's a cubed plus b cubed, we would factor it as a plus b. So you'd cube root the a cubed, and you'd cube root the b cubed to get a and b. And then once you have that a and b, the pattern is you're going to square the first term, you're going to multiply the two terms together, and then you're going to square the last term. That's kind of the formula. That's how I remember the formula. So we square the first term, so that's a squared, minus, we multiply the two together, ab, and then we square the last term, so that's b squared. And notice the signs. We have a plus, a minus, and a plus. The next one, the a cubed minus b cubed, we would have a minus b, similar to what we just had, but the minus, it goes in the first spot, the a minus b. And then same thing, same pattern, you square the first term, plus you multiply a and b, plus you square the last term. So that's the factorization pattern. Again, notice the signs will switch. So the signs in the first one is plus minus plus. The sign in the next one is minus plus plus. You only ever have one minus, only one negative when you have these. And also notice this part, this trinomial, is not factorable. Trinomial not factorable. That's because it's not a perfect square trinomial, though it might look like one. So let's use these patterns on 8 and 9. 9 will be for you as we try this. But for 8, solve with the cubic factoring formulas above. So solving this, we would factor first. We have to figure out what our a and b is. So we would take the cubed root of 8 cubed. That would be 2x. So that's our a. And then we do the cubed root of 125, and that's 5. So our a equals that value, and our b equals that value. So we would factor it like this. We take this one and this one, so that would be 2x plus 5. And then we square the first, so that's 4x squared, minus. Multiply the two together, the a and the b, so that's 2x times 5 is 10x. And then square the last term, so that would be 25. Equals 0. So that's how we factor that. We would set both of these equal to 0, and solving on this side, we'd subtract 5 and divide by 2. So one solution is negative 5 over 2. Notice that since it's cubed, we should have 3 solutions. This is a degree 3, exclamation point. So we should have 3 solutions. So we found one so far. That's this one. We need one more solution, or sorry, 2 more. Like I said above over here, the trinomial that you get is not factorable. So don't try to factor this. You could try, but it's not going to really get anywhere. So you have to use the quadratic formula, QF, quadratic formula. So using the quadratic formula, we would have the opposite of b. b is negative 10 here. X equals 10 plus or minus the square root of the discriminant, which is b squared minus 4 times a times c, all over 2 times a, so that would be 8. Go ahead and pause the video, see if you can simplify that. We've done these before. Pause the video and see if you can get those final simplified answers. So I got all the way down to 10 plus or minus square root of negative 300 divided by 8. 300, we could probably Yeah, so the square root of 300 is square root of 100 times the square root of 3. So it would be 10 root 3. So this would be 10 plus or minus 10I root 3 all over 8. And 10, 10, and 8 are divisible by 2. So that would be 5 plus or minus 5I root 3 over 4, dividing by 2. So we get, did we get 3 solutions? We have 2 solutions here. There are 2 imaginary solutions. And we have 1 rational solution here. So that is 3 solutions that we found. Don't be surprised when you have to use the quadratic formula. You will pretty much always have to use the quadratic formula here. So when you're attempting number 9, keep that in mind. So that's to try this. On to number 10, factor by grouping to solve. And I noticed I forgot on this document that it equals 0. We actually did this in the previous video on the previous page. So when you have 4 terms like this, you do what's called factor by grouping, which is what we have done many times before. We group the first, group the last 2. Take a greatest common factor out. So that would be x to the 4th. You're pulling out an x to the 4th. So that would be an x squared minus 5. And then we'll pull out a negative 4. That'd be an x squared minus 5 equals 0. And you know you're doing this process right when you have identical binomials. So we'd have an x to the 4th minus 4, x squared minus 5 equals 0. And something I notice here is that this is a squared term, but this is an x to the 4th. So that x to the 4th minus 4 is actually factorable again. That's a difference of 2 squares. Difference of 2 squares. That guy right there. So we can actually write it as x squared minus 2 and then x squared plus 2 times x squared minus 5 equals 0. And then we can set each one of these equal to 0 and solve. Doing this makes sure that we don't miss any solutions, because we should have, notice, we should have 6. This is a degree 6, so we should get 6 solutions. So we'd have x squared equals 2, so x equals plus minus root 2. There's 2 solutions. X squared equals negative 2, so x equals plus minus I root 2, because the negative there. There's 2 more solutions. And then we have x squared equals 5, so x equals plus minus root 5. So there are 6 solutions. We have 2 rational, 2 imaginary, and 2 rational, or irrational, sorry, 2 irrational. 4 total irrational solutions and 2 imaginary solutions for that one. And if you would solve number 11, I will caution you that you should get 6 answers. And be careful that you type them as we ask in Schoology, like putting the rational, the real, the imaginary in whatever order that we ask you to. All right, let's look at our last question, number 18. Number 18, you're designing an open box to be made of a piece of cardboard that is 50 inches by 32 inches. You will form the box by making the cuts shown below and folding up the sides so that the corners are squares. You want the box to have the greatest possible volume. So first thing, volume of a box. The volume of a box would be the length times the width times the height of the box. So that's good to know. Write a polynomial function v of x for the volume of the box and find the maximum volume. So depending on how much x you cut out of each corner, the volume is going to be dependent on how big of a cut you make. Like if you make the cut this big, you're not going to have much cardboard left. It's probably going to be a really small box. But if you made the cut real small, then you would have a bigger volume, but it might not be the maximum volume for the box. So if we made these cuts along here, and we don't know how big to make the cut, but we'll say it's x inches for each of these cuts. And then we fold, right? So all these corners are gone now. So you have a shape that looks kind of like that. and then we fold, we're going to get a box. So this side of the box, that side of the box it was 50 inches, but we cut 2 x's out, so that would be 50 minus 2x. This side of the box, it was 32 inches, but again, we cut x out of each one, so that would be 32 minus 2x. And then the height of the box is actually one of these x cuts. So if we wanted to find the volume of the box, the volume with respect to how big our x cut is, we would have x height, we'd have 50 minus 2x as one of the dimensions, and then 32 minus 2x as the other dimension of the box. So this is our volume formula for the box. Now we could multiply that all out, but what I'd like to do is something different. I'd like to do a quick sketch where our x-axis, this is x, the length in inches of the, we'll call it the corner cut, how much we cut out of the corner. And then this side is the volume, that axis is the v, the volume. So what I would like you to do is to go on to Desmos and type this formula in, and then find, using Desmos, find what is the maximum volume and what length x would it take to get that maximum volume. So let me show you really quickly a couple tips about using Desmos. So I went to Desmos, desmos.com, and the calculator option, the start graphing, big blue button I think it was, and we want volume with respect to x equals, and our formula was x times 50 minus 2x times 32 minus 2x. And you'll probably see just a vertical line in red. Mine's red at least. So we have to go up here to this top right and click Graph Settings. And we helped you on our paper, if you have the notes printed out. We want the x-axis to go from about 0 to 18, and we want the y-axis to go from about 0 to 5,000. And now you can see what the maximum is of this part of the polynomial function. So you'll have to graph that and get the exact x that leads to that exact maximum value. Don't round it. We want exact answers here. And this is just part of the polynomial function. If we zoom out, you'd be able to see a little bit more. That is our polynomial function that we graphed. It's a cubic function. It's x cubed. Since it's three-dimensional, it's a box, it's a volume, it's a cubic function. It has 3 directions. It has a high point and a low point. But all this stuff over here, if we zoomed over here, this wouldn't make a lot of sense in the context because we're talking about a volume and you can't have negative volumes. And likewise, you probably can't cut that much out of a corner of a box. I don't think you can cut 25 inches from each corner and still have cardboard left over. So really it's just this middle part that we're looking at on the polynomial function. But do that on Desmos and that'll be your last try this. Hope you have a great day. See you next time.